Beneath one of the world's busiest stretches of ocean, there is a tunnel, not a bridge, not a ferry crossing, a tunnel, drilled through solid rock beneath 75 meters of open sea, stretching for 50 kilometers, carrying high-speed trains at 300 kilometers per hour between two countries that spent centuries trying to conquer each other. And here's what nobody tells you. The engineers who built it had no GPS, no real-time satellite guidance. They were digging from both ends simultaneously, England drilling east to west, France drilling west to east, through complete darkness, through solid chalk, through water, pressure that would crush a human skull, and they had to meet in the middle with an error, tolerance of just a few centimeters. In 50 kilometers of underground drilling, they pulled it off, and the way they did it is one of the most extraordinary engineering stories in human history. And by the end of this video, you'll never look at the Channel Tunnel the same way again. Most people think they know the Channel Tunnel story. Big machines, long tunnel, trains go fast, England and France connected, done, and sure. At surface level, that's accurate. But here's the crack in that thinking. When most people picture tunnel construction, they picture someone digging a hole, maybe a big hole, maybe with fancy equipment, but fundamentally just digging. Scoop out the rock, put it somewhere, walk through. What the Channel Tunnel actually required was something categorically different. The engineers weren't just digging through rock, they were navigating through geology they didn't fully understand, managing water pressure that varied unpredictably, steering machines the size of houses through complete darkness, using surveying techniques that pushed the limits of what was physically possible, and doing all of it under 75 meters of open ocean, with no ability to stop, pause, or start over if something went catastrophically wrong. 3 questions this video answers today. How do you steer a machine the size of a building through 50 kilometers of solid rock and hit a target you can't see? What was actually happening inside the chalk beneath the English Channel that made this tunnel possible, and what almost made it impossible? And what engineering problems did they discover after the tunnel opened that nobody had predicted? So let's go deeper than anyone has ever taken you before. Let's start with the geology, because this is where the Channel Tunnel story actually begins, and most people completely skip it. The English Channel sits on a bed of chalk, not the chalk you write on a blackboard, but marl chalk, a specific geological layer of soft, relatively dry, relatively impermeable rock that was laid down about 70 million years ago, when the English Channel was the floor of a warm, shallow sea. This chalk layer is what made the Channel Tunnel possible. It's soft enough to cut through quickly, hard enough to hold its shape without constant reinforcement, and dry enough that water infiltration is manageable rather than catastrophic. The engineers knew the chalk was there. What they didn't know, couldn't know until they started drilling, was exactly how consistent it would be. Chalk layers vary in thickness, density, and water content. Hit a zone where the chalk becomes wetter or weaker, and your tunnel boring machine, a rotating cutting head the size of a house, can get stuck, flood, or lose accuracy. The tunnel boring machines, called TBMs, were each about 9 meters in diameter and weighed around 1,200 tons. Think of them as enormous steel worms, chewing through rock at about 10 to 15 meters per day, installing concrete lining segments behind them as they went. 11 TBMs were used in total, 6 going from England, 5 from France. Each one had to follow a precise route mapped from surface surveys and borehole data, staying within the chalk layer, avoiding zones of geological instability, and threading between the seabed above and harder rock formations below. Now here's where it gets genuinely extraordinary. Each TBM had a laser guidance system, but lasers only work over line-of-sight distances. In a curved tunnel stretching tens of kilometers, you cannot simply point a laser from the entrance and expect it to reach the boring face. The Earth curves. The tunnel curves. The laser can only see so far. So engineers developed a relay guidance system, essentially a chain of laser and surveying stations installed progressively throughout the tunnel as it grew, each one feeding position data to the next, each one checked and recalibrated constantly against known reference points. But here's the part that nobody talks about. The biggest threat to accuracy wasn't to accurate equipment failure, it wasn't the geology, it was temperature. Rock expands when warm and contracts when cold. In a tunnel environment where the TBMs generate enormous heat, the surrounding rock temperature fluctuates constantly, and those temperature fluctuations cause the tunnel lining itself to shift by fractions of millimeters constantly, invisibly. Over 50 kilometers of tunnel, those fractions of millimeters add up. Engineers had to build temperature compensation into every single surveying calculation, correcting for thermal expansion in the rock, the lining, and the measurement equipment simultaneously. When the English and French TBMs finally met in December 1990, the vertical alignment error was 58 millimeters. The horizontal alignment error was 356 millimeters. Over 50 kilometers of underground drilling under the sea. Those numbers are considered an extraordinary engineering achievement. Here's what the textbooks say about the channel tunnels. Engineering challenges. Water pressure, distance, cost overruns. All true, all interesting, but what they almost never mention is what happened on the night of November 18, 1996. 2 years after the tunnel opened to the public, a HGV freight shuttle train caught fire inside the tunnel. Not a small fire, a severe fire. Temperatures inside the freight wagon reached over 1,000 degrees Celsius. The fire burned for 9 hours. 34 people were trapped in the tunnel. Shuttle staff and truck drivers who had taken refuge in the service tunnel, running between the two rail tunnels. Nobody died. Not a single person. And the reason nobody died is something engineers had built in from the very beginning. But that, most passengers who use the tunnel today have never heard of. The Channel Tunnel isn't 2 tunnels, it's 3. 2 large running tunnels for trains, one in each direction, and a third, smaller service tunnel, running between them along the entire 50-kilometer length. This service tunnel has its own ventilation system, its own emergency lighting, its own pressurization. It's maintained at slightly higher air pressure than the rail tunnels, so that in the event of smoke or fire, air flows away from the service tunnel rather than into it. Every 375 meters along the tunnel, there are cross passages connecting the service tunnel to both rail tunnels. These are the evacuation routes. When the 1996 fire broke out, passengers and staff walked through these cross passages into the service tunnel and were protected from the fire and smoke by that pressure differential. Wait, it gets even more interesting. After the 1996 fire, engineers discovered something that hadn't been fully anticipated in the fording. The chalk lining of the tunnel had been damaged by the extreme heat in ways that took years to fully assess and repair. The chalk, which had been so perfectly suited to tunneling, turned out to be vulnerable to thermal shock at fire temperatures. Sections of lining had to be rebuilt. Monitoring systems had to be upgraded. The Channel Tunnel didn't just survive its first major crisis. It taught its engineers things about underground fire behavior at scale that had never been studied before, and those lessons have since shaped the design of every major undersea and underground tunnel built anywhere in the world. Here is the most shocking fact in this entire video. The Channel Tunnel was built under the sea in underground sea, 80s and early 1990s, before GPS was publicly available, before modern computer-aided surveying existed in its current form, before engineers had any real-world experience building a tunnel of this length under open water. Every single problem they encountered, they were solving for the first time. Every solution they invented became the foundation of modern tunnel engineering. You've probably never thought about what it actually feels like to be inside the Channel Tunnel on a train. You're traveling at up to 300 kilometers per hour. You're 75 meters below the surface of the sea. On both sides of your carriage, there are approximately 40 centimeters of concrete and rock. Then the English Channel pressing against the outside. The concrete lining is continuously monitored. Sensors embedded in the tunnel wall measure pressure, temperature, and movement in real time. The entire tunnel management system tracks air quality, fire sensors, electrical systems, and train positions simultaneously. If a sensor triggers anywhere in the 50-kilometer system, a response protocol activates automatically within seconds. That level of integrated monitoring didn't exist before the Channel Tunnel needed it. The systems developed to run the tunnel became the blueprint for modern infrastructure, monitoring, the same sensor network approaches now used in bridges, skyscrapers, and subway systems across America and worldwide. Your city's most advanced infrastructure monitoring systems trace their technical lineage directly back to the engineering problems that the Channel Tunnel forced engineers to solve. Now, this same principle of pressure differential safety design, using a slightly higher pressure environment to prevent contamination from spreading, is exactly how hospital, operating theaters, and pharmaceutical cleanrooms work. A positive pressure environment pushes contaminants out rather than letting them in. The Channel Tunnel's service tunnel uses the same physics to keep smoke out during emergencies that hospitals use to keep bacteria out during surgery, and this is just the beginning of how deep this goes. Now here's something that most people never connect to this topic. The Channel Tunnel was proposed, planned, abandoned, reproposed, replanned, and abandoned again over a period of nearly 200 years before it was finally built. Napoleon Bonaparte first proposed an undersea tunnel between England and France in 1802. He even had preliminary engineering drawings made. The proposal collapsed, partly due to the war resuming between France and Britain, and partly because the technology simply didn't exist to build it. In 1880, the first actual boring attempt began on the English side. Workers dug over a kilometer of pilot tunnel near Dover before the British government stopped the project on military emphasis. They were afraid a tunnel would allow France to invade England. The same concern killed the project again in the 1970s, when construction was partially started and then halted. Think about that. The engineering challenge wasn't what stopped this tunnel for almost 200 years. The politics were harder than the rock. Think of the Channel Tunnel like a stubborn bridge that humans kept trying to build between two neighbors who couldn't quite decide if they liked each other enough to share a front door. The rock was always there. The chalk was always suitable. The technology became available in the 1950s, but the tunnel didn't happen until 1988, because engineering is only ever half the problem. The other half is whether the people on both ends actually want to be connected. So here's what we uncovered today. The Channel Tunnel was drilled from both ends through 50 kilometers of chalk under the sea, meeting in the middle with an error of less than 40 centimeters, using relay laser surveying and temperature-corrected calculations without GPS, in complete darkness under open ocean. Its three-tunnel design, with pressure differential safety corridors, saved 34 lives in the 1996 fire, and established the blueprint for emergency safety systems in every major tunnel built since. And it was technically feasible for over 100 years before it was built, delayed not by new engineering limits, but by 200 years of political disagreement between two countries that share 50 kilometers of chalk. The Channel Tunnel isn't just a tunnel. It's proof that the hardest part of any engineering project is never the engineering. Now I want to know, did you know the tunnel had been proposed since Napoleon's time, and would you take a train through it? Drop it in the comments right now. In our next video, we're going somewhere that makes the Channel Tunnel look straightforward. We're going to find out why Japan built an entire airport on an artificial island in the ocean, and why that island is sinking, and why engineers knew it would sink before they even started building, and built it anyway. The world is not what it looks like on the surface. It never was. This is Logivra, and the logic was always there. You just needed someone to show you where to look.